Hi, and welcome to my channel, JaberTime. I'm gonna go over graphs of exponential functions. Today I have enough examples. I have my notes and I wrote some and I highlighted some just to try to save you some time and cover enough material. Let's get started. Graphs of exponential functions, a very good example to start with, which is 2 to the power x. And that sometimes we refer to it as doubling. Has a lot of stories in history and examples in life, but anyway, to stay focused, 2 to the power x, that's what we have. That's called exponential, and it is growth. The graph shows it, and let's support the graph. One thing that you want to keep in mind is 0, 1. 0, 1 is something that you want to pay attention to, which is right there, this point right there, the y-intercept. It's kind of critical, especially when you shift the graph right and left. You gotta pay attention to this point and drag it. Here's my function written again. When x equals 0, 2 to the power 0 is gonna be 1. So my ordered pair will be 0, 1, which is right there. Anything raised to the power 0 is 1. That's one of the rules. Let's plug in 1. If you plug in 1 here, 2 to the power 1 is 2. So we have 2 to the power 1, which is 2. So the order pair will be starting with 1 for x. We came up with 2 for y, or as an output, right there. 2. 2 to the second is 4. So 2 is my input. My output was 4, right there. 3. 3 is my input. 2 to the power 3, 2 times 2 times 2 is 8. So my output is 8. 3 will take me up to 8. As you could see, every step I move right, it takes me more up. That's an exponential behavior, not linear. Let's go to the left because it's sometimes interesting and it's a good to practice and pay attention to when it's negative. So this is going to be 2 to the power negative 1. But we have another math rule that says a to the power minus m is the same thing as 1 over a to the power m. So you kind of take the reciprocal and make it. For example, 10 to the power negative 2 on your calculator is not going to give you negative 100. Because sometimes that's what I get back. So 1 over 10 to the power 2, which is 1 over 100, which is 0.01, 100ths. You could test it on the calculator to support this concept. So 2 to the power negative 1 is actually 1 over 2 to the power 1, which is just 1/2. So that's going to be negative 1 as an input, and output will be 1/2, which is right there. Negative 1 to the left, just half going up, halfway before you reach 1. Okay, what else we could talk about this graph? This graph shows that we are having a horizontal asymptote, which is the x-axis. Differently, we call it y equals 0. It doesn't touch the x-axis. Alright? It looks like it's touching right here. No, but that's not true. It keeps getting close and close, but doesn't touch. Okay, that's graph number 1. The other way around will be called 1/2 to the power x. So, and the previous one, I'm gonna support that in a lot of different ways. The base here is 2, which is more than 1. That's called exponential growth. Here it's exponential decay. Notice that the base here is half. Okay, so let's just keep it focused on my notes, then I'll explain more as we go, because there is more pages that talks about the base and more. So for the convenience, I have it written right here, 1/2 to the power x, x equals 0, you plug in 0 here, and I said earlier that anything raised to the power 0 is 1, so 0, 1. Right there. plug in 1. That's half to the power 1. It's not gonna go anywhere, so it's gonna just be half. So 1 will take me to half, and right there. Let's go to the left. We don't want to check all the points. That's enough points here. Negative 3. 1/2 to the power negative 3. It's what I mentioned earlier, the reciprocal when you have negative exponent. So what you need to do is apply the negative 3 here and apply negative 3 here and take the reciprocal differently. That's 1 to the power negative 3 over 2 to the power negative 3. Take the reciprocals. That's 2 to the power positive 3 over 1 to the positive 3, which is just 2 to the power 3, which is 8. So negative 3 will take me all the way up to 8. And that's right there. Of course, the horizontal asymptote is the x-axis, or we just write in short horizontal asymptote as y equals 0. Now, we had two examples. One had half as a base and the other one had 2. In general, they look like this, where b is positive and does not equal to 1. Of course, it doesn't make any sense to have 1, because imagine if you have 1 to the power x, you're not going to go anywhere. It's going to stay horizontal with the value of y equals 1. It's not going to be negative. You could try it, but I'm not gonna I'm trying not to make the video like more than what it's supposed to be, because if I keep going off, I'm gonna add another 10-15 minutes. But just give you a quick comment why it cannot be negative. When you have a negative number as like negative 3, as you raise it to the power 2, to the power 3, to the power 4, and multiply it by itself.
Jared Cron, come to the main office. Jared Cron, come to the main office.
This was on the announcements. I'm at work. As you could see, I'm in my classroom. I'm trying to find time to record without any interruptions, but it's really tough. Anyway, back to the video. Trying to stay focused and save you some time. So when you have negative 3 times negative 3, when you go like to the second, it's gonna change to positive. Negative 3 times negative 3 times negative 3, it's gonna stay negative. So the outputs will be up and down, up and down. That's not what we want. Okay, it's gonna fluctuate between positive values and negative values. So anyway, to stay focused, I have two types. The first example was y, if you call it just y, equals 2 to the x. You remember that? That looked like this. The second one on our list was half. Different y, let's call it y1 and y2, half to the power x, which is decay. This is growth, exponential growth, and this is exponential decay. Now, they all share a lot of things. The horizontal asymptote is the x-axis, which is right there and right there. They are both called one-to-one function. That means invertible. And one-to-one function, they pass the horizontal line test. See the horizontal line? Like the vertical line test. They pass it, which means any horizontal line that you graph, it doesn't cross the graph more than once. Domain, all real numbers. Let's write it this way, all real numbers. Or you could write negative infinity to infinity. Range from 0 up, not including 0. From 0 up, not including 0. From 0 to infinity. Differently, just to support that, comes from the y values, y greater than 0. The x-intercept none, you're not going to cross the x-axis. The x-axis is called a horizontal asymptote. So we got that. The y-intercept, that's a major point to pay attention to, and I mentioned that earlier, 0, 1. And that is also 0, 1. Unless if there is more into it, like if a number up front here is 4, like in the coming example, it's going to go through 4. Though we talked about this, so let's move on. Increasing if b is greater than 1. Increasing if b is greater than 1. This is called increasing. and since b is greater than 1, b is equal to 2. This one right here is this part decreasing since b is less than 1, and b in this case is half. That b is the base, that b is half right here. I think that should do it for this page, but that's how we could describe exponential growth and exponential decay without any shifts or effects. That is growth. We talked about that. B greater than 1. A good example was 2 to the x as an example. Here's an example of decay. Notice that here they made it clear b is greater than 0 and less than 1. In other words, fractions like half. You don't want to be 0 because you're not going to have any function. That goes up. It's going to be flat horizontal axis as x-axis, and you don't want it to be 1 because you're going to be horizontal at y equals 1. You don't want to be negative because you're going to go up and down. Fractions only. Okay. Now, sketch the graph of f of x equals 0.25 to the power x. 0.25 is a quarter, which is 1/4. That's another way to look at it. Then you want me to state the domain, range, and asymptote. One more time. I know I'm going a little bit fast maybe, but you get my point, guys. I'm trying to organize my notes to the best that I can to cover enough material in less time. And I'm doing all this because I don't want to flip the page if it says state the domain and range and asymptote and I forget and move on. That's not right. That's why I have it right here, to keep me focused and to keep you with me in less time. In person, that's not my style. I have more time in person in classrooms, but while I'm recording video, I try as much as I can to stay formal. It's kind of hard to talk about jokes and joke around and do other things. I know I'm talking off, but sometimes off topic, sometimes I have to. Just want to let you know that just talking, adding and subtracting and graphing, that's not my personality. That's teaching. I'm just trying to teach and stay constant, but that's not me. That's not JaberTime. JaberTime is a different topic. All right, let's get back. So my function f of x equals 1/4 to the power x. X equals 0, plug in 0 here. Anything raised to the power 0 is 1. We talked about that. Anything raised to the power 0 is 1. So when you raise this to the power 0, you get 1. So 0, 1. 0, 1. 1/4 to the power 1 to get the output is just 1/4. Kind of hard to graph it by hand, but I'll do my best. This is halfway. This is 1/2 of that, which is 1/4. -1. We have to kind of see how to deal with negative exponents. So that's going to be 1/4 to the power -1. Apply the formula or the rules that says the following. Take a look. A over b to the power m is a to the power m over b to the power m. So I'm going to do that. Then I'm going to apply another formula, which is 1 to the power -1 over 4 to the power -1. There's another formula that says if you have negative exponent, you could take the reciprocal and make it positive. So I'm going to take the reciprocal of that, or flip them. In other words, that's going to be 4 by itself. 4 to the power 1 over 1 to the power 1, which is just 4. The light turns off because I'm not moving, but I'll just keep recording, okay? You know what? Let me turn it on. This way you could see that I'm not just like... Okay, back to this. I think it's better to keep it on, and it's hard to keep it on if I'm not moving because it's controlled by a sensor. Alright, now, where are we? -1/4, -1/4. So that's mine. To graph it, it's kind of hard without tilting the paper, so I'm gonna do my best because I don't want to be tilting papers and recording. I don't want to go off the frame of the recorded video. Alright, trying to stay here to show you that this is a horizontal asymptote, but I think you got the point. Now domain or real numbers. Range will be from 0 to infinity, not including 0. Horizontal asymptote will be the x-axis or y equals 0. That should do it for this one, and we are on example number 1 only. That's the graph in detail. I don't have to put it there, but in case if you want to pause the video and look in detail, because by hand it's not going to be clearly accurate unless if you zoom in and slow down. But anyway, we got it. Okay, now when we talk about vertical shift, so the original function is in orange 2 to the power x. I want to shift it up 3 units. That's called vertical. So if I take it up 3 units, one way to mention it, this point was a major point, as I mentioned, critical point to pay attention to, 0, 1. I'm pointing to it right there. Well, if you are at 0, 1, move up 3 units, you'll be at 0, 4. And then from there, graph it. Same thing for this one. This one here, you go down 3 units from the original. This is the original, about the same, except I need to take it down 3 units. So if you're at 1, you're going to be at -2. 1 unit will to the x-axis, 2 more units to make it a total of 3. So you are there, and you graph it. Now, one comment that I would like to mention here: if you are standing at this point and you want to move up, you could imagine or think about the x-axis, which is y equals 0, as a horizontal asymptote is going to move with you. So looking down from this point, you are far by 1 unit. So from this point, you have to look down 1 unit to locate the horizontal asymptote. From 4 looking down 1 unit, you will be at y equals 3. Hopefully that helps. Alright, so that's from -2 going down 1 unit will be at -3. That's your horizontal asymptote. Now here we are talking about horizontal shift. So we're going right and left. My original function is 2 to the x, going through 0, 1 again, and it's doubling. It's the exponential growth. When you subtract 3 from x, not from outside, here it was from the original y. This is like my y, and here I'm subtracting from all of it. So it's like y equals 2 to the x, and this is a new y, which is the old y, subtracting 3. That's the concept. I'm subtracting 3 from the original y values, where here I'm subtracting 3 from x. If it's not clear, this is what it says, 2 to the power x minus 3. So when you affect x by adding and subtracting, you're moving horizontally, as it mentions. Subtracting 3 means move it right. Move this point to the right 3 units. Instead of being at 0, 1, you're going to be at 3, 1. Makes sense, right? 3 units. Here, by adding 3, you're going to move left 3 units. Adding 3 to x, of course. 0, 1 will be at -3, 0. The horizontal asymptote stays the same in all of them. And we're done. Now here, graphing a shift of an exponential function. Example number 2, graph f of x equals 2 to the power x plus 1 outside -3. So what's happening? I have 3 different colors. To get to that, which is my main function, I'm going to start with the basic one. The basic one is 2 to the x. We know it. 0, 1. Plug in 1, you get 2. Plug in 2, you get 4. And so on. You could plug in negatives, but you're going to deal with fractions. Let's leave it. So my graph roughly looks like this. But I want to make these clear. Alright? Now, let's go green. and refer to y2, which is the same except we are adding 1 to x, so we're gonna move it left 1 unit. So this is gonna be here, this is gonna be here, and this is gonna be here, and roughly that's my graph. Let's go now red. Now I'm gonna take this one, which is right there, down 3 units. So this, the green one, down 3 units. From 4 it's gonna be at 1. That's 1, 2, 3. And this one, just stay focused right there, and this one right there, and that's my function. Now pay attention. Do you remember when I mentioned that this is my major point or my main point? Looking down from this point, I see the horizontal asymptote right there. Okay, so that moved here, then moved here, so that is the point. In other words, this is my looking down my horizontal asymptote. So just to be careful not to cross it. So the domain is all real numbers again. Range is from -3 up to infinity, and horizontal asymptote is y equals -3. I think that should do it. I could add more to it, but I think basic symbol is enough. I don't want to make it distracting or more. I could test it with plugging the points. So maybe you could do that if you want. If you plug in 1, I'm saying you get 1. And okay, I'll do it quickly without writing. 2 to the power 1 plus 1. That's 2 to the power 2, which is 4. 4 minus 3 is 1. Yes, 1, 1. That's this one here. 1, 1. Okay. As you can see, I could just keep talking, but I prefer not to. To support the graph. So that's without the original steps. But I think it's better to do it step by step together with the different colors. This is an interesting problem that needs a graphing calculator. So I'll show you how to do it. Approximating the solution of an exponential equation. Solve 42 equals 1.2 times 5 to the power x, that's my base, plus 2.8 graphically, round to the nearest thousands. So if I rewrite this right here in 2 different colors, 42 in red and this right hand side in green, I'm gonna call this one y1, I'm gonna call this y2. So I'm gonna go to the graphing calculator and graph it. Now before I go to the graphing calculator, I have this designed and made to help you. I believe this is exponential growth because b is 5, which is greater than 1. So my graph somehow is gonna look like this. Now this is not gonna be 0, 1. It's gonna be the starting point, which is a in this case. But that's not our concept. We still have to shift it up to 2 units. Without that, that's gonna be 1.2. So that's not our part exactly. Where's this point, which I could find it on the graphing calculator for you, since I'm gonna use it. Staying focused. Here's my y2. y2 is horizontal line because it's fixed at 42 all the time, and it's not graph to scale, as you could see, just to give you a concept, an idea. So this is y2 and this is y1. Where they meet is where they are equal. That's what we're trying to find. How much is this x up to the nearest thousands. Now I'm telling you how to fix it and make the window from -5 to 5 on the x scale and y minimum from -5 to 50. Let's see if I could make it fit on the screen, and we'll go from there. Here's my graphing calculator, and I wanna start from scratch. I did it, that's why how I picked these numbers. Let's do zoom standard, which is number 6. Number 6 means you're going from -10 to 10, from -10 to 10. So kind of boring, but it's a good start. From -10 on the x to +10, from -10 on the y to +10 if you count those tick marks, because we're going by 1. All right, now let's go to the y. My first function will be this right here. So I'm going to write 1.2 times, open parenthesis, times 5 to the power x plus 2.8. My second function is flat 42. Graph. You're not going to see everything because that's standard view. As I said, go to the window, and you don't want to have -10 to 10. That's a waste right here, and that's a waste, and that's even a waste right there. You don't need to see all this. So that's why kind of starting at -5 to the right up to 5. From y minimum, -5 is fair enough. I don't want to go all the way to -10. And y maximum, I need to go beyond 42 so I could meet 50, and 50 will cover 42 and will show it to me. So 50 will be a good choice. Graph. That's my y1 and that's my y2. To find the intersection, let me point to it using the pencil. Right there you see the calc. Calc has a lot of different features that you can do. One of them is intersection. So let's go to it. Since it's blue, hit the second, go blue, and intersect is number 5. Now I am on y1. It shows right here, and it shows that I am on y1. The curve that's supposed to be exponential growth. Move to the right till you get close to the point of the intersection. I passed it, as you could see. I want to go back. I want to go back. I even passed it now at this level. By hitting enter, it's gonna jump from y1 to y2, which is this horizontal line. Take a look. Enter. Yes, it doesn't look like I jumped, but it is, and I'll show you once I move right. Look, instead of going up like before, it's moving right because it's on the horizontal line. I passed it, as you could see. Try to get close to it as much as you can to be more accurate. When you hit enter, it says guess. That means get closer to it to be more accurate. Just do it, you'll be fine. So what do I have? I could read it from the screen about 2.166 because they want me to do thousands. I think that's good enough. I don't need that one here. Even if it's rounded, that's still not enough to make the 6 7. So that is when x equal. And that should do it for the graphing calculator. Moving on. This right here says sketch a graph of fx equals 4 times 1/2 to the power x. As you could see, I mentioned earlier, it goes through 0 1 0 1, and we've done this without the 4. With the 4, let's see what's going to happen. Plug in 0, I get 4 times 1/2 to the power 0, which is 4 times 1. Anything raised to the power 0 is 1, which is 4. So the order pair is input 0, output 4. Right there. It's not 0 1, it's 0 4. So whenever you have something like that, which is y equal a times b to the x, and if b is greater than 1 as exponential growth, you are looking at this type of look of an exponential growth function where this point is 0a. That's your initial amount, sometimes what we call it a. Okay, when x equals 1, I have 4 times 1/2 to the power 1. That means 4 times 1/2. 4 times 1/2, or 1/2 of 4, which is 2. So my input is 1, my output is 2. 1 will take me to 2. You could tell that it's a decay. We're going down. -1, let's go to the left. 4 times 1/2 to the power -1. We know how to do this. We've done it before in this video. So I'm going to apply it and flip it. So it's going to be 4 times 2 to the power 1, which is 8. So a -1 will take me up to 8 up here. To graph it, something like this. The main concept is to show you here that you are actually dealing with a different type of graph. We keep saying 0 1 0 1. Today it's 0 4. That's what you need to pay attention to. Of course, we don't want to forget the domain range and asymptote. That's why I have them. And here we go. The domain is all real numbers, left and right. The range is from 0 to infinity. It did not move. The horizontal asymptote still the x-axis or y equals 0. Alright, that's detail about the same graph, which is 4 times half to the power x. We talked about this, this, and this. And the horizontal asymptote right there, so we should be fine. Reflections about the x-axis. When you wanna take the original function 2 to the x, which is right there, and you wanna reflect it about the x-axis, all what you need to see or do is, for the equation, have to see the minus here. Why is that? So roughly speaking, if this is not called f of x, if it's called y, I think this one is like y, but with a minus. So this looks like minus y, correct? Because that's my y. Look. So when you have the minus up front, instead of being up, you're going to be down, and that's called reflection about the x-axis. Just keep that in mind. Of course, the horizontal asymptote is going to stay there, and we are fine. Reflection about the y-axis. When you go about the y-axis, you're going from right to left, from left to right. So I think it does make sense to see the x being replaced with minus x. 5, negative 5. 4, negative 4, you know. So that's the difference between reflection about x or reflection about y. Writing and graphing the reflection of an exponential function. We have a function given to me which is f of x. We want to find a new one called g of x by doing the following: reflecting f of x equals 1/4 to the power x. We've seen it before, about the x-axis. So when you go about the x-axis, you're gonna change the y values from positive to negative. So that should be minus f of x, formally speaking, which is minus 1/4 to the power x. Find and graph. So we're gonna find and graph. I found it, then we're gonna graph it. Let's do some math first, quick. When x equals 0, 1/4 to the power 0, that's 1. So 0 will take me to 1. 0, 1. When x equals 1, 1 to the power, 1/4 to the power 1 is 1/4. So 1 will take me to 1/4. 1 will take me to a smaller number, 1/4. Negative 1 will be 1/4 to the power negative 1. Flip them. You're going to end up with 4 to the power 1, which is 4. So negative 1 will take me to 4, and right there. Graph it. Somehow looks like this. This is the new equation. We're going to reflect it about the x-axis. So the new equation, I'll use green for it since I'm using green here. That's going to be down there. That's going to be right there. Instead of 0, 1, it's going to be 0, negative 1. Instead of negative 1, 4, it's going to be negative 1, negative 4. And that's fair enough. Domain, range, and asymptote. Okay, let's finish it right here. Domain, all real numbers. That's for the new one, g of x. Range, since we're going from 0 down to negative infinity, differently, to write it clearly, we go from negative infinity up to 0, not including 0. That's how we write it down. Or, of course, same concept as y less than 0. Horizontal asymptote, because we are not talking about vertical asymptotes, we don't have them. Still the x-axis, which means y equals 0. Okay, we're almost done. That's my graph using software. Just to support. This measure 1 was 0, 1. This is 0, -1, which is right there. Okay, last question. Writing a function from a description. Write the equation for the function described below. Give the horizontal asymptote, the domain, and the range. F of x equals e to the x. That's a measure function that we are familiar with in pre-calculus, calculus. Is vertically stretched by a factor of 2, step by step. 2 times e to the x. That's stretching it. Reflected across the y-axis. So it's going to go about the y-axis. So x changes from, let's say, 5 to -5. So the minus goes for the x. And then shifted up 4 units. Outside, we're going to add 4. Now, to be clear about these here, this is what I have. The original one was just like this. That's my number 1. Let's call this one y1. When you reflect it about the y-axis, it's gonna look like this. So if this is 2, this is still 2. So down below you, because e to the power 0 is 1 and 2 times 1 is 2. When you do this problem, or shift it up 4 units, so I have 2, 3, 4, 5, 6, and let's say 1. 1, 2, 3, 4, 5, 6. From 2 go up 4 units, you're going to be right there, and you're going to look like this way. So where is the horizontal asymptote? The horizontal asymptote, looking down here, it's 2 units below you as a measure point. 2 units below you, you're going to be right there. So here we go. Domain, all real numbers. Range will go from 4 up, and horizontal asymptote is y equals 4. That should do it, and I'll see you in the next one. Thank you.
Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.